Okay, so we are continuing our discussion of section 8.7, the very important Taylor and Maclaurin series. Very, very important material. And these power series, these functions, like they're representing these functions as power series with corresponding radii of convergence is a very important. It's a very important in math, and many engineers refer to these formulas. So formulas have been created over the years for important Maclaurin series and their radii of convergence. And in the ebook, this is table 1. Now, what I've done is I've actually created a handout that has the Maclaurin series and actually intervals of convergence in it as well, along with some other formulas. So let me show you where that is. One moment. Let me go into the. Okay, does everybody see the course content here? I'm in course content chapter 8. Who's seeing that okay? Is it showing up all right? Okay, good. Thank you, Jacob. Thank you, Abadar. Thank you, everyone. So if you go to section 8.7, Taylor-Maclaurin series, there's a handout. There's a link to a handout that I am sharing with you. Just click on the link there, and I'll click on the link, and let's just see. Okay, so I got to show it to you separately. Please download my Maclaurin and Taylor series handout. Okay, so what's this handout look like? Well, let me show you. One moment. Okay, this is the handout. One moment, let me get another view up here. Hold on. Give me one moment here, class. Yeah, this will be better. That's what I want. Okay, so are you seeing the handout okay, class? Okay, excellent, excellent. So of course you have access to these formulas on your final exam, right? But I thought it would be convenient to have the formulas like sort of all in one place, you know. And so I have, like at the top here, I have the Taylor series formula. And then below, I have some important Maclaurin series formulas with their intervals of convergence. This table, so like the table in the book gives radii of convergence, but I think it's important that you have the interval of convergence, because just because you know the radii, the radius of convergence, doesn't mean that you exactly know what x values for which the power series converges and equals its function. You know, unless of course the interval of convergence is from negative infinity to infinity. You know, if you have a radius of convergence that equals infinity, then you know your interval of convergence it's all x values. But for the other series that have an interval of convergence that is like restricted between two finite values, I think the interval of convergence is better to have. So that's there. And then at the bottom, there is a formula called Taylor's inequality, And Taylor's inequality we're going to talk about on Thursday. That goes with section 8.8. So that being said, what we're going to do, you see, we can actually make use of these formulas. Okay, just like we made use in section 8.6, we made use of the formula for 1 over 1 minus x, which incidentally, its Maclaurin series is the same as the formula you learned from section 8.6. But just like we made use of that formula to help us do a variety of problems, we can make use of these other Maclaurin series formulas to help us do a variety of problems. So let's get right to an example here. Let's work with an integral. Okay, let's work with an integral. So here is one, and I'm going to do an integral of the sum of two functions. The integral goes from 0 to 0.2, and we want to evaluate this integral, this definite integral, correct to within 5 decimal places. Now, offhand, class, do you know the antiderivative for the arctangent of x cubed plus the sine of x cubed? Do you offhand know the antiderivative? Okay, Renat says no immediately. That's right. And the antiderivative doesn't exist. To my knowledge, there's no explicit antiderivative for the arctangent of x cubed, and there's no explicit derivative for the sine of x cubed. Now, I don't know all, there are tables of integrals. You had some practice with tables of integrals back in chapter 5, right? So I'm not saying the antiderivatives don't exist, but to my knowledge, I'm not aware of them. Let's put it that way. But we're going to utilize power series or Maclaurin series to help us with this problem. So how are we going to do this? How are we going to do this problem? Well, of course, we could try to find the Maclaurin series for the arctangent of x cubed and the Maclaurin series for the sine of x cubed. Now, the Maclaurin series is centered about a equals 0 for both of those functions, right? The Maclaurin series would be the power series centered about x equals 0 or a equals 0. And that would be okay to use in this situation because your limits of integration go from 0 to 0.2. And those values are pretty close to a equals 0. But what we could do is we can make use of the Maclaurin series that we already have. So like the arctangent and the sine, all right, those two, we have Maclaurin series for the arctangent and the sine. Okay, so use your zoom feature on the right to blow up the page if you need to. Here is the arctangent. Here's the Maclaurin series for the arctangent of x. And you notice the interval of convergence falls between -1 and 1. All right. And then here is the Maclaurin series for the sine of x. And for that Maclaurin series, the interval of convergence is from -infinity to infinity. Well, our limits go from, in our integral, go from 0 to 0.2. And so that falls within both intervals of convergence. So it's okay to use power series representation. So that being said, let's go ahead and make use of these Maclaurin series. So on the next page in our solution, what I do is I state the Maclaurin series for the arctangent of x. Okay, I state it right there. So let me get my stylus out here. And I should have naturally I should, hold on here. I can put my interval of convergence here. All right, and so if the arctangent of x has this power series, then the arctangent of x cubed, we can just substitute in x cubed where the x goes. Okay, so this is similar to the idea, you know, if you know the arctangent of x, then the arctangent of an apple is equal to the series where n equals 0 to infinity of -1 to the nth power times the apple to the 2n plus 1 power all over 2n plus 1. And of course, you know, your apple would have to be between -1 and 1. So what I'm doing here when I go from the arctangent of x to the arctangent of x cubed is I'm just making use of this formula here. Okay, are there any questions on that? It's similar to what you did in section 8.6. So, okay. So I don't have to, because I have a formula for the arctangent of x, I can make use of that formula to get, well, I'm sorry, because I know the Maclaurin series for the arctangent of x, I can make use of that Maclaurin series to get the Maclaurin series for the arctangent of x cubed. I don't have to go through and formally derive the arctangent of x cubed. The arctangent of x cubed will equal this power series right here. N equals 0 to infinity, -1 to the nth power times x to the 6n plus 3 power over 2n plus 1. And I can do a similar for the sine of x. We know the power series for the sine of x. From there, I can get the power series for the sine of x cubed. Recall that in my integrand, the integrand, I had the sum of the arctangent of x cubed plus the sine of x cubed. Now, what will happen in WebAssign, by the way, is for the problems where they want you to use existing power series to help generate other power series, they will provide a table for you along with the problem. Okay, please let me know if you have any questions before we move forward here. Incidentally, that handout, the handout that I showed you in the course content for section 8.7, I will make sure that for your final exam, I'll make sure that handout is part of your supporting documents, okay, for examining, okay. All right.
Will you make a note that we can have a hard copy, or do you prefer us to just look at it on the screen?
I would prefer, Maria, that you just look at it on the screen.
Okay.
Okay, good question. Okay, are we ready to move to the next page? Are there any questions? Give me a thumbs up if you're ready, and we'll proceed on. Okay, good. Maria's good. Okay, Tall's good. Excellent. Jacob's good. Okay, Baraka's good. All right. And I'll wait for one more person here, and then we'll move forward. Okay, excellent, excellent. Thank you, Leping. Thank you, Thomas. Okay, well, now that we're armed with our power series, we can proceed to get a power series for this integral here. Okay, so let's proceed on. All right, so now what I do is I substitute in for the arctangent of x cubed and the sine of x cubed, I substitute in the corresponding power series. And I have to figure out how am I going to get a power series for this problem. Well, first thing I recognize is that I have the integral of the sum of two power series. Well, the integral of a sum is the sum of the integrals. So that's what I do on the this step here. Okay, I'll go slow here. I want to make sure you're following me, okay? Okay, but now these integrals individually, I have, like for the first expression here, I have the integral of a sum. Well, that's just equal to the sum of the integrals. So I write that this way. And same thing for the second integral. I have the integral of a summation, the integral of a sum. That would be just then the sum of the integrals of all the terms in the series, right? I mean, isn't this some of the most beautiful math you've ever seen? I mean, look at this math. But now, okay, now I have to proceed to integrate. Well, remember, in each, like in the first integral, we're integrating with respect to the x variable. So that means -1 to the nth power over 2n plus 1 is treated like a constant, and that can be brought out in front of the integral. And for the second expression here in this, the second power series, the -1 over 2n plus 1 factorial, that can be brought out in front of the integral. Let me just kind of circle everything here. And you've seen this kind of thing in kind of math in section 8.6 when we talked about 8.6 last Thursday. Well, the antiderivative of x to the 6 to the power 6n plus 3 is just x to the 6n plus 4 over 6n plus 4. And same for the other integral. Yes, Jacob, question? And then we have our constants of integration. So every you know, you're finding you're taking the sum of a bunch of indefinite integrals, right? And every indefinite integral has a constant, but you can combine all those constants into so you get like just one constant, you know, and that's what the constant C1, and then for the other summation constant C2. Okay, now for this problem, the C1 and the C2, I could define C and let C equal C1 plus C2, right? I could combine those constants. Let me ask you about the power series. These two power series, intuitively, what do you want to do with these two power series? What do you want to do with them?
Can you factor out the x terms?
Well, before we do that, your intuition's good, Maria. We do want to factor out, like we see that both of those power series have in common x to the 6n plus 4 divided by 6n plus 4. But before we do factoring, what intuitively do we want to do with those two power series? We want to make them, I'm trying to.
Into one?
Yes, that's right. Good, Maria. We want to combine those two power series. Oh, can we do that? Can we combine the two power series? Is that possible?
Is that a yes?
Well, it's either a yes or a no.
I'm going to go with yes.
Okay, and why? You're right. Why, class, can we combine those power series? Well, look at the first power series. First power series starts at n equals 0. Second power series starts at n equals 0. They start with the same index. So that means we ought to be able to combine those power series as one. You see? If the second power series started with an index like n equals 1, we would have to rewrite the second power series so it started at n equals 0. The power series, in order to add them, they have to have the same starting index. Okay? Are there any questions on that? Well, Nathan, what I'm saying is I'm not saying that I don't know if the first power series is like if, I mean, these power series, we don't necessarily want to say one power series is less than another. I mean, it's like you're looking at two functions, right? But what I'm trying to say is what I'm trying to say here is that I want to combine this power series here with this other power series. And I'm able to do that because both power series start off with the same beginning index, n equals 0. And what I'm saying is, let's say the second power series started out with an index like at n equals 1. Okay, so see the index for both power series is at n equals 0. So we can just add those power series. But if the second power series, if its starting index were different, like n equals 1, then we'd have to readjust the second power series so its starting index were n equals 0, and then we could add them. But these two power series are good. They have the same starting index, and we can add them. All right, so let me show you on the next page then. Who's ready to go to the next page? Give me a thumbs up, and we'll. Okay, wonderful, wonderful. Okay, so on the next page then, okay, again, I'm rewriting my integral here. That's going to equal then, if we combine the power series, we're going to get this summation right here. And we're going to do what Maria suggested. We're going to factor out. I mean, it makes perfect sense that we would want to factor out a common factor. Both, so x to the 6n, sorry, I don't know, that happens sometimes. X to the 6n plus 4 over 6n plus 4 is common between both terms. So let's factor it out. Let's factor it out and write the power series for the integral, or indefinite integral now. I'm working with an indefinite integral, so there's a constant of integration. The power series, I'll write it this way. Please let me know if you have any questions. Okay, now I have a question here for you. There's a negative 1 to the nth power here. Hold on. I factored that out. I don't know why it's doing that. I factored also, incidentally, the negative 1 to the nth power out as well. That was in common between both of the terms. The fact that we have a negative 1 to the nth power in our power series tells us that what kind of series will this power series be?
Alternating.
That's right. And when you hear alternating series, you think alternating, what theorem do you think of when you hear alternating series? You remember? If you have an alternating series and you're trying to estimate, that's right, Nathan, the alternating series estimation theorem. And so we're going to use that to help us. Remember, our definite integral, we want to estimate that correct to within 5 decimal places. So we're going to use the alternating series estimation theorem. Okay. Now, incidentally, if the terms of the series, the power series, were all positive, we would have to use then we'd have to use another approach. Okay, but we got an alternating series here, so let's use it. Okay, so I'll go to the next page if we're good. Okay, so here we go. My integral grows from 0, our limits go from 0 to 0.2. So I'm going to then write my definite integral. Well, I mean, let me just go back, hold on. The indefinite integral is equal to this power series. And so for the definite integral, all I need to do is substitute into the power series 0.2 and 0, right? And that's what I do here. There's no constant of integration anymore. We have a definite integral now. So we don't have that constant of integration. And I have to substitute in 0.2 and 0. Now, substituting in 0.2, that's right here for x. And if I substitute in, one moment here, class. Okay. If I substitute in, okay, so here's the x. I'm going to substitute in first the 0.2, which I do here. And then I'm going to substitute in the 0, right? I subtract, and I substitute in the value of the power series with 0 for x. But that's just going to give me 0, right? If I put 0 in for x here, every term is going to equal 0. So this is now the power series for my definite integral. And you notice the x variable is gone now. It's just a regular series like you learned back earlier in chapter 8. It's not a power series anymore. And so we're going to use the alternating series estimation theorem. We can do that because for this series here, the terms of the series are clearly getting smaller with n. And they're decreasing, and the terms of the series approach 0, and we can use the alternating series estimation theorem. Now, we wanted our answer correct to within 5 decimal places. So that means the criteria I have to use is 5 over 10 to the 6th power. And what I do is I keep numerating terms of the series until I reach a term that is smaller than 5 over 10 to the 6th power. Okay, so correct to 5 decimal places means I'm going to use the criterion of 5 over 10 to the 6th power. If it were correct 6 decimal places, I would use the criterion 5 over 10 to the 7th power. Okay, for example. Well,
So
it
in
turns
this case, you only need to use one term.
That's exactly right. That's exactly right, Maria. Very good. Because the second term is less than 5 over 10 to the 6th power. So amazingly, we only need one term. We only need one term of this series. And remember, it would make sense you wouldn't need too many terms because the indefinite integral, the limits are from 0 to 0.2. So, if it were like from 0 to 0.8, you might very well need to use 2, 3, or 4 terms. Who knows? Um, so this reads here, by the way, 0.00080 is greater than 5 over 10 to the 6th power. Back when these methods were developed in, the calculus was invented by Newton in the 1700s, or actually, I guess, what, 1600s, really. Wait, I should know that, but you know what I mean. It's over 300 years ago. And these ideas were developed, over 300 years ago. And this is how mathematicians, when they wanted to compute things, they didn't have TI-84 calculators, right? So this is how they did it, And even now, yes, we have computers and calculators, but they rely on algorithms like this to get answers, right? There's programming behind these computers and calculators. All right, I'm going to go to the next page if there are no questions. So it turns out then that because the second term of the series is smaller than 5 over 10 to the 6, then as Maria said, we can approximate this definite integral correct to 5 decimal places with just the first term. Okay, and therefore, and the first term, by the way, the first term, right? This here is just equal to 2, right? So the first term is 0.2 to the 4th power times 2 divided by 4. And so by the alternating series estimation theorem, our definite integral value is approximately equal to 0.2 to the 4th power times 2 over 4, which is 0.0080. And that's correct to 5 decimal places. Okay. But in fact, you're actually correct to 7 decimal places. In fact, it's even better than that, because that second term, which was 0.0000000512, that's less than 5 over 10 to the 8th power. So your estimate's even better, Absolutely amazing. Absolutely amazing. And I'll comment one thing. I'll make a comment here. I'll go back to this page. But this, computing this here, okay, computing this estimate is something that mathematicians can do. Like, it's simple math. Simple math. A computer can do that, right? Computer can multiply, divide, add, and subtract, like the flops. And a computer could do this. Humans could do this easily. Okay, so, so when, like, Jeff Bezos and them, they go to outer space, they need to thank the mathematicians from long ago who developed these ideas, right? Because they're used in engineering and math. They're used. Computer science, it's a wonderful time to be in math and science. We have computers now that can handle computations, and it's just a wonderful time. How many think this is absolutely fascinating? Okay, Renard likes it, Jacob, Nathan, Abidara. Wonderful, wonderful. Thomas, great, great. Very important material for your final exam, section 8.7, right? Very important. Are there any questions at all? All right, well, I will stop the recording then.